Hello everyone and welcome to the third lecture for ME 296. This lecture is going to introduce resistors as components rather than as a concept. We're going to go over Ohm's law and we're going to go through some examples of how to use Ohm's law. First up, resistors, the component. Resistors are a passive component that when current is flowing across them cause a loss of energy from one side to the other, and that energy is typically lost in the form of heat. The schematic symbol is shown on the right of the screen. You should all be familiar with this, having passed 196. So let's go through a couple of common types of resistors and their preferred uses. One of the more common ones is the wire-wound resistor, and these are made by winding wire around an insulating core. These are not typically used in alternating current devices because due to the winding of the wire and the wires being next to each other in the coil, you have some parasitic inductance and capacitance, and these can cause some issues when dealing with alternating current. More in-depth discussion of capacitors and inductance is going to happen in the next couple of lectures. These are usually reserved for high power and high precision devices. Now, the reason they're preferred for high precision devices is because we can know their resistance very well. And this is because most metals have a well-known resistance value. And if we know the resistance value to a high degree, and we know the length of the path to a high degree of accuracy, we can determine the effective resistance very accurately. Another common type is the carbon film resistor. These are made by taking a cylinder or some other shape and then depositing a thin carbon film on the surface of this shape. Then a laser or something else is used to cut away portions of the carbon film that was deposited in order to form a path that current has to flow through the carbon to get from one side to the other. These are fairly accurate, and they also have a very small parasitic capacitance and inductance. So these are very common in both AC and DC circuits. So some common properties of resistors is how they behave as a response to certain parameters. And one of those is the operating temperature. Outside of a certain range of temperatures, resistors can sometimes have very different values. But luckily for us, the face value of a resistor is given in terms of room temperature, which is 20 to 25 degrees Celsius. And within that range of temperatures, we can assume it's fairly constant. It's only when you get to the extreme temperatures, like it's on fire or we've put it in ice water, that the resistance will change significantly. Something that might be more relevant to the circuits that we're going to be building in class is the maximum voltage drop and the power rating. The maximum voltage drop is the most voltage that can be lost across the resistor before it starts to break. And this is related to the power rating of the resistor, which is the maximum power that can be dissipated by the resistor. So where that comes from is that we know that the electrons are traveling through the resistor and they lose the energy, and that energy is turned into heat energy, and it's got to go somewhere. If the heat cannot be radiated away from the resistor fast enough, it's going to keep getting the resistor hotter and hotter, and eventually it will melt or burst into flames or something quite spectacularly sometimes, as you can see from that little picture there. Fortunately, this probably won't happen unless we've done something very, very wrong, but we're going to try not to do that because safety is very important to us. And then one last thing about resistors is color bands. Because resistors are often quite small, we can't simply write the value of the resistor and the tolerance of it and all the other important properties that we might need on the side. We'd have to carry magnifying glasses everywhere. That's just not workable. So the solution that was settled on is the color band method, where each band has a specific meaning for what the value of the resistor is. There are a couple of different styles, but they all convey roughly the same information. Each color represents one of the 10 digits, 0 through 9, and where they're placed tells us which value it's going to be in the value of the resistor. So just a quick example, because you can study this chart later to kind of work out some of the finer points, but a quick example is going to be a resistor that has color band pattern red, yellow, gold, gold. We can interpret that to mean it has a face value of 2,400 ohms and then the actual value is going to be within 5% of the face value, or within plus or minus 120 ohms. So it's important that they give us that tolerance value, because manufacturing techniques are not perfect. So everything is going to be within a range of the ideal value that they were going for. And these different tolerances tell us whether or not something is going to be useful or not for our circuit. Of course, we always measure first so that we know if it's going to work or not. But if you're in a hurry and you're just prototyping something, sometimes these tolerance bands can give you a real good idea of whether or not your circuit isn't working because of something you did or because the resistor just isn't correct. All right, so now we're going to start with Ohm's law. So the analysis of circuits begins with Ohm's law. Everyone should already know it. I'm just going to go through it relatively quickly and a little bit of the history. So the first formulations were actually set down by Cavendish. His procedure involved touching batteries of increasing strength and then writing down how much it hurt. And then he discovered that if a battery is twice as strong, it hurts twice as much. And he discovered that there is a linear relationship between the battery strength and the voltage and how much current flows through an object or a resistor where he himself was the resistor. Unfortunately, he didn't share this with very many people, so it kind of stayed private among him and a couple of his colleagues. But luckily, a bit later on, Ohm used a galvanometer, which is an early form of ammeter, to perform similar experiments, but instead of shocking himself, he used the galvanometer. And he discovered that the current read by his meter was proportional to the temperature, the length of the wires in his setup, and a constant that could be fit. Now, this is the beginning of Ohm's law. So if we're taking the temperature to be constant and we're taking the length of the wires to be constant, everything in there is a constant, right? So that reduces it to its more familiar and modern form, where the resistance is a constant of the material. What it's saying in physical terms is that the voltage between 2 points is equal to the current and the resistance between those 2 points. Or the resistance times the amount of electrons we're trying to get through it is equal to the amount of energy it takes to get from one side to another side of that device that we're trying to get the current through. So it's very important to remember that voltage is the potential energy between 2 points and not at a single point. If you measure the voltage drop across a wire, there's no resistance through there, so you're going to get 0. And if you're trying to measure the voltage difference between the same point and it's going to give you 0. It's not meant for that. It's for between 2 points that have some resistance between them. Now, this equation completely describes resistive circuits. And then later on, we're going to see that Ohm's law applies to circuits with reactance instead of just resistance, which is coming up a little later in alternating current. Now we're going to do some examples real quick. So we're going to find the current given the other two values. The larger side of the voltage generator symbol traditionally emits the current, so the current's going to travel in a loop around the circle as shown. Without an explicit ground, we're going to take the smaller terminal of the voltage generator symbol to be ground, or 0 volts. And since there's only one resistor and wires themselves do not lose voltage when we're dealing with circuit diagrams, all the voltage is going to be lost across the resistor. So we can use Ohm's law and the given values to determine that since we want current, we're going to rearrange Ohm's law to I is equal to V over R. And given that voltage is 5 volts, R is 10 ohms, we're going to get 5 volts over 10 ohms, or half an amp. To determine resistance, we're going to use the same circuit setup, but we're going to change the values a little bit. We know that current is 1.2 amps, and we don't know the resistance. Following the same logic as the previous example, all 5 of the volts must be lost across the resistor. And all of the current must pass through the resistor, since it's not a parallel circuit, it's only in series. So we're solving for resistance using Ohm's law. We've got resistance is equal to voltage over current, or 5 volts over 1.2 amps gives us 4 ohms. Remember that significant figures matter, and while current had 2 sig figs, voltage only had 1, so your final answer should be given with 1 significant figure. And then the voltage example. Same setup. We don't even have to rearrange Ohm's law this time. Voltage is already equal to resistance times the current, and we're given 1 kilo ohm and 0.2 milliamps. Multiply them together and we get the voltage across the circuit is going to be equal to 0.2 volts. And the final example with a very slight hiccup. We're going to define the ground as being after the output of the voltage generator. The current still is going to flow in the same direction, but now we're going to define 0 to be the output. So what does that mean? That means that the rest of the circuit after ground is going to have some negative voltage because current still has to flow. But that's fine, remember, because it's a potential energy and you can have negative potential energy. Perhaps this circuit is defined to have 0 there because it makes it more convenient for a larger, more complicated circuit that we have to solve at some other point. But the important part is it's fine to have 0. So using the given values and solving for voltage, don't have to rearrange anything. We determine that the voltage is negative 2.4 volts across the resistor. We can take this as a positive number if we're still talking about how much voltage the generator is generating. But when talking about voltage across the resistor, we should remember that it started at 0 and then dropped lower because we lose energy going across resistors. And it will, if you were reading this with the digital multimeter, you would also see a negative voltage across the resistor. All right, so that's all for this video. Thanks for watching.